Payés. He's actually doctoral student in the first year. And actually this came out of a nice story because he came to Japan just to stay for a month. And because of the coronavirus, he ended up staying 6 months. And so he had to do something during the 6 months. And so I suggested him to work on this project. So in that sense, also this project it starts really from basics, and I think it will be very easy to understand to most of you. Anyway, so the main interest here is you have a two-dimensional wedge. By a wedge I mean that you have, for example, some sort of cone in 2 dimensions of certain angle alpha, and you have Brownian motion, which is reflected here at the 2 edges, and then you are trying to do simulation of this stochastic process. Anyway, so just to start, reflected processes. So processes, as I said, that like Brownian motion that lives in a certain domain, but they are restricted by these 2 boundaries, appear in many applications, which not necessarily are completely physical. Sometimes they also appear, interestingly enough, in other fields, which at the beginning you might not think they are related to this problem. For example, one of the main fields which actually is very much interested in this kind of processes is queuing theory. In queuing theory, what happens is you study the behavior of queues, and then when you take limits, essentially you end up with certain type of reflected Brownian motion. Anyway, what I'm trying always to tell people in the past few years is that when you study these kind of processes, actually there are 2 aspects of the process. One is the reflected process, and the other one is the stop or the kill process. And the difference is, as I said, the reflected process keeps moving after hitting the boundary, while the stop process is only valid until the first time you hit the boundary. Okay, so that's the difference between a stopped and reflected. And in many cases, these 2 processes are related, and our objective today is to discuss, density formulas related with these 2 processes, and to try to study simulation algorithms, or if possible, exact simulation algorithms. So simulations that can actually simulate what is the position of the process at a certain point in time. Okay, and even when you are going to start this study, you already understand that there is a difference between simulation of reflected and stop, and the difference is at the corner. Why? Because if you have a process that is stopped and the process decides to enter the corner, you know that the possibilities of stopping the process increase. But if you are instead doing reflection, you understand that you might have a problem because the reflection process might stay a long time reflecting on the 2 boundaries near the wedge, or the point O. Okay, and so in fact this problem appears a lot when you are trying to simulate exactly these processes, and in many cases the simulation time becomes infinity, and therefore you have to study the complexity of your simulation method and maybe discuss some approximations. So this is going to be our goal for today, to discuss all these issues. By the way, if there are any questions at any point, just stop me at any time, and then I'll try to answer the questions. Okay, so this is more or less the plan that I plan to cover today. I just discussed the abstract. Then I start first with 1 dimension for students, and then I will try to discuss a 2-dimensional reflection principle. Then I will discuss a simulation algorithm, the complexity of the algorithm that I propose here, and then I try to generalize to certain type of SDEs. in all this story, there's a very interesting part where history plays a role, and this is something that I will discuss also through the different results. Okay, so let's start first with one dimension, and I think many students learn the distribution of reflected Brownian motion or a stop Brownian motion, or some people call it kill Brownian motion, by something that is called the reflection principle. I will try to recall this very briefly in the next slide, but I also want to say that actually the reflection principle in PD theory is usually called the method of images, okay? And I will also try to say why is this, but this is going to become important later. But anyway, something that is interesting is that the final formulas are exactly these two. And here I introduce some notation. WT will always be Brownian motion. In this case, there is an X here because it starts from X. And this tau 0 here is the first time that the Brownian motion hits 0 because I am in one dimension. So I'm supposing that instead of having 2 dimensions, this is time and this is space. And so this is the first time I hit the boundary. So this is tau 0. And when you consider a reflection, the name of the process is xtn, which means that it continues. Okay. So this is X, and here, this is just W here. Anyway, the final result actually can be written in many different ways, but one way of writing it is actually this way here that I have used. This is the law of the stop process, and down here below, I have written the law of the reflected process. I have tried to write them as similar as possible, just to try to explain to you this duality or this sort of parallelism between these two formulas. So what you can consider here is actually the probability of the Brownian motion at time t and the fact that it's positive. So the same quantity appears in both probabilities, except that in the case of a stop, you have this minus sign, and in the case of reflection, you have plus sign, okay? And this should be more or less clear. Why is it so? Because in one case, you are asking what is the probability that the process, so let me redraw now my picture here. So in the first case, you're asking what is the probability that being at time t, I have started from X, and my Brownian motion has not really hit the boundary. Okay, so this I should actually have done this in blue because this is a stop case. And in the reflected case, you might have this blue, but you can also have these things which are reflected. So just very naturally, you understand that the amount of blue paths will be much less than the amount of red paths, because the amount of red paths will actually include these blue ones too. So this is one way of first understanding the difference between the red and the blue. But actually, then there is so in that sense, I mean that there is a symmetry. And one of the questions that I have been always interested in is how long this symmetry remains. And I suppose everybody has an opinion on that. And of course, I would like to hear that once I finish my talk. But anyway, so one way of understanding this now in the sense of paths is that you could say that in the red one, you are using all the trajectories, including the trajectories that touch the boundary, while in the blue one, which are the stop ones, you have to subtract all the paths that actually touch the boundary. And that's one way of understanding this plus and minus. But of course, there is the classical reflection principle, which actually tells you the same story. Okay, so I wrote this here, and actually I think my colors have been reversed, and now I know it's okay, they are correct. So I planned to do it like this. So everybody learns that all these paths that you need to delete, you can do reflection principle, and they are characterized as all the paths that end in the reflected piece here. Okay, so you take this distance A, you take the distance A, and then you compute it, and then that's how the plus and minuses appear. Okay, so this is the one-dimensional case, and now we go into the setting of the problem for 2 dimensions. So as I said before, you have a wedge of angle alpha, and just for simplicity, I will assume that it's in between 0 and pi. And then you have a Brownian motion that starts at the point X, and this is the Brownian motion, and the time at which you touch the boundary is going to be defined as tau. Okay. Now, X, as always, X will denote the reflected process on the wedge. Okay. Now, for the moment, and for most of the talk, I actually will assume that WT is non-correlated Brownian motion. So the components are independent. W1 is independent of W2. And actually, there is a lot to discuss about the correlated case, and this is something that is actually quite interesting to discuss later on in the talk. But anyway, so the general result for Brownian motion reflected in a wedge is due to Varadhan and Williams, which is a very, very interesting paper, which actually states the following. In order to characterize reflection in 2 dimensions is different from reflection in 1 dimension. Why? Because in 1 dimension, the only possibility is if the process touches the boundary, it has to become positive. That's the only possibility. In 2 dimensions, you observe that actually the process could actually move in different directions depending on what is the behavior at the boundary. And in this paper, actually, there is a characterization of what kind of reflections you can have so that the process is alive, and in what kind of situations the process will actually end up hitting the vertex and will not be able to get out. And let me just show you one example so that you understand what I mean. Suppose that your reflection is always of this type. Then you understand that the Brownian motion once it starts centered here, and if by any reason it hits the boundary, it will start getting closer and closer to the vertex and will not be able to leave. So the right conditions for oblique reflection are actually written in this paper. Okay, but for the moment in this article, we only consider normal reflection. So normal reflection means that if I have these 2 boundaries, I will always reflect in this direction and in this direction. Okay, all right, so this is going to be our situation. So I take the normal vector and I take the normal vector, and these are the directions of reflection. Now, so the way this process is characterized, and I will write it here, is as follows. So xt will be equal to the Brownian motion plus something that I may call the local time. Okay, so it means that this local time actually should satisfy the following formula. It should have 0 to t indicator of xs being in the boundary of the wedge. So this domain is called D, okay? And then I will have n of nx and then dls. So this LT is actually an increasing process. Increasing meaning that it could stay constant for a while. And this formula here, it actually says that it only grows when the process L is at the boundary. Okay, and when it grows in the direction n. So this is what we mean when we say that the reflection is normal. So this is normal reflection. Okay, so if you wanted to have oblique reflection, like in the case of Varadan and Williams, essentially you have to change this n by some vector field gamma of xs. Okay, that's all. So this is the characterization of reflected Brownian motion. Is the Brownian motion itself plus some increasing process that will only move along the direction, the normal directions at the boundary, and it will only act when the process X is trying to exit the domain, when the process X is at the boundary. Okay, so that's the characterization as a stochastic process of the process X. Okay, now let me try to explain to you how the density of these things are obtained in the literature. And actually, this is something that I only learned recently, and it was a quite interesting thing because me being in the applied side of things, I only knew this paper by Iyengar, sorry, it's quoted twice, but it's Iyengar, who used the method of images. So it means that actually he did not do things using probabilistic methods, he used PD theory. And today I'm also going to use it. But anyway, so is the method of images, which I will explain, is almost like the reflection principle. Okay. Now, this paper was taken by Metzler in 2010. And he said, well, the formulas in Iyengar, some of them are wrong. And so he corrected them, and he also used them to apply it to credit risk problems. In credit risk problems, actually the problem is not reflection, it's a stopping. Okay, the first time that the value of a company is so low that it will go bankrupt. The first time that something bad happens is the first time that something good happens. So Metzler and Iyengar do not discuss the reflection problem. And I was always wondering why, and I thought that this was a good problem for a good student. That's why I proposed it to Pierre Bach. But anyway, later on, I discovered that actually these formulas were known a long time ago. And these were two Australians, actually. So it's Kaslow and Jäger. They wrote a book in 1959. And in 1959, they already wrote the Laplace transforms for these problems. Okay, but so this is a kind of an interesting story. But anyway, this is how these sort of formulas evolve. And actually, I will also add a little bit more later on. But anyway, so it's not strange that these formulas probably were not well known even before Kaslow and Jäger. But anyway, so that's the story. And so how is it done? Because this is the part that now is interesting to me because I want to do simulations. Well, the argument is as follows. It's at the beginning, you don't start with any angle alpha. You start with a certain particular type of angle alpha, which is pi divided by a natural number, not zero. Okay? And then you define these sort of reflecting type operators. So essentially, if you want the reflection principle for this kind of domains is something like this. I have a path that is crossing here. And so if I want to reflect it, essentially I have to move it like this. Okay. And the principal idea here is that the probability of this black path has to be the same as this probability of this joining black and red path. Okay. And you have to use this in order to try to compute the probabilities. So this will be more or less the method of images explained for a probability student without going through PDEs. Of course, this very quickly becomes much more complicated once you say, oh, but wait a second, what happens when now my path starts to go here and it ends up here? Then you have to realize that going here corresponds to this guy being here. And then you have to fold. This is like folding a space. Many copies of spaces, you have to fold them at the end into this domain D. And this is why it's called the method of images. And this is what is really interesting. Now, the reason why we take M to be a natural number is because then the number of transformations that you need in order to cover all the space exactly is only from 0 to 2n minus 1. Okay, so it means that if you continue doing this, you will keep having partitions of the space and they will fit exactly. If alpha is not of this type, then of course you will not be able to fold the space nicely, and you will end up with a piece of this folding here. Okay, and this is what is interesting later on, because we want to deduce a formula for not for alpha equal pi over m, but for a general alpha. Okay, our goal is that. But you will see that the simulation method that we will use is actually based on this alpha equal pi over m. All right. So this is the reflection principle. And so here I explain again the domain. So you have that the operator tk maps d into dk. So it will map a copy of this space into this space, or into d into d2, etc., etc. Okay. And because the angle is exactly pi divided by m, then you can do this. All right. So if you do this folding and you start counting, as I said, the formulas for stopping and reflecting are not so difficult to obtain. It's very easy. So this one is the formula for stopping, which is the formula that you find in Iyengar. And this is the formula for reflection. And if you compare the two formulas, you see that the formulas are very, very similar, except for this factor here, which here is a 1. So I want you to remember what I said in one dimension. In one dimension, you have to discount the paths in a certain way. You have to take away the paths. In this case, it depends on which copy of the domain you are, okay? Because if you are, for example, here, you start to discount of this path here, but then you have to take in account that you have also discounted the path that went into D2, and so you have to add them. That's more or less the idea, and that's why this is an alternating series, okay? Of course, you can take this in a totally different way and say, okay, I believe these formulas. I want to check that actually these are the solutions for the associated PDEs that are related with the densities. Okay, the associated PDEs, and here I'm only going to talk about the case of reflected process. The associated PDE is as follows. You define the expectation of the reflected process through a test function f, and I define this to be the function u. So this function u satisfies the heat equation. Remember, this is the heat equation in 2 dimensions. Then you have this initial condition. This initial condition appears because when you take here t equal to 0, then you have the u0x is equal to the expectation of f of x0. And of course, f of x0 is constant, is f of x. And then this is the condition that replaces in probability this local time condition. You remember that I wrote this condition here. Okay, so you see the parallel. The normal vector here is here. The fact that you have to be at the boundary is here. okay? And this derivative here is associated with the Ito formula for this process, which is of bounded variation, okay? And so this is called the Neumann condition. Okay, so once you have this PDE and you know that this PDE characterizes uniquely the reflected Brownian motion, you can say, okay, I'm going to take this formula here, just plug in there and verify that everything is satisfied. Okay.
Oh, so excuse me.
Yes.
Is this because L is in? I mean, is this equation because the in the integrator? I mean, it should be ds. I mean LT.
No, no, no. This is the condition. This is the condition
For
that
LT.
the local times. Yes, this is LS. This is DLS.
Oh.
Well, we can discuss that later, but if you want, you see, I have already written it here. Here, you remember?
Oh, yes.
So
okay.
it's DLS.
Okay.
Okay. Okay. So and so you can do this, but actually, and this is something that Pierre had to suffer a lot with. It's not so easy to do the verification. Okay. In particular, you need to verify the boundary conditions, and some of these boundary conditions are a little bit hard to verify, as we will see. Anyway, now here comes the the strange part of all this story. For of course, Pierre being a student, I would tell him, okay, right now these are the general formulas, and this is more or less how Iyengar explained this in his paper too. He says, okay. He works only with the stop process, okay? And he says, okay, now the formula for the stop density in the general case now is general alpha. So this is not necessarily true that alpha is pi over m. And Iyengar tells you, oh, this is the formula, okay? And then you look at his proof. Well, it's not really a proof. But he says, okay, what you have to do is you take this function, you plug it into this PDE, okay? Plug it into this PDE, and you will see that everything is satisfied. And so Pierre tried to do that, and actually proving that this thing satisfies the boundary conditions is not so easy. It's actually a little bit of a mess, okay? And so we were trying to understand how you could understand this formula in some other way just by saying, okay, it's a hint. I don't know what kind of hint, but then we decided to study the problem a little bit more, and the hint is as follows. Well, this IN that appears here is a special function, and it's the so-called Bessel function. The Bessel function is the solution of this second degree equation, and it has an explicit formula, which I'm not going to give, but anyway, it's just a series formula. And so the way to understand heuristically all this, if you want, one way of understanding this formula is that if you look at this part here, this is almost the Gaussian part, okay? Because usually when you try to look at Gaussian processes or Gaussian laws, essentially you have something like this. Okay, and if you understand that y is equal r to the ei theta and x is equal to r0 ei theta 0, I'm trying to use complex notation, but you have to understand that essentially I'm saying that it's two coordinates, cosine theta, sine theta, and cosine theta 0 and sine theta 0. So if you plug this in here and you try to expand it, you will find this term here, okay? And then sort of, you will also find some extra terms, which are e minus rr0t, which are these guys here. And then you will have certain cosine functions here, which are related with theta 0, which are these guys here. So for you to understand this horrible formula 5, if this is the first time that you look at it, is almost like saying these guys here are almost like the norms of x squared plus y squared, and these guys here are the cross terms. Well, something like this. This is very heuristic what I'm doing now, but this is so that you get some idea, okay? Of course, there is this factor 2r and t over alpha, but I will rather explain this some other day. But this r, for example, appears because of the Jacobian of the polar, the change of coordinates for the polar, and this alpha appears because your angle is an angle alpha, okay? And of course, the t is because it's two-dimensional. Okay. So the way to understand these formulas, and now I will explain all these heuristics through a simple case, is I will go back into these formulas that I obtained here. I will take this one here, and I will change it into polar coordinates. So if you change it to polar coordinates, you actually obtain this formula, which actually explains what I'm just trying to say. Okay? So if you say, again, that y is equal to r ei theta and x is equal to r0 ei theta 0, what you obtain is this formula here. So you see these are the cross terms. Okay, these are the cross terms. Now here is a big trick, which I should say is still a little bit of a mystery to me, but I find very interesting, which is you use this formula here, which is an expansion of the exponential, of this exponential here, in a base of polynomials, which is the Chebyshev polynomials. Okay, the Chebyshev polynomials, essentially what they do is they say that Tn of gamma is actually cosine of, if I'm correct, n gamma. Okay, but these are polynomials on cosine of gamma. Okay, so essentially what you have to do is you have to expand this thing, and then the polynomial that results out of that is what is the so-called Chebyshev polynomial. Now, once you do that, and these I0 and In that appear here are the Bessel functions that I talked before, then you plug this equality, you plug it here. Okay, you plug it here, and now what you have to do is you have to do Fubini. You take this sum and you plug it here. That sum becomes this guy here, because I just told you that this is cosine of n times the angle, and this formula has this form. And that's how you obtain this famous formula here, which now you could call it 4 or 5. The deduction is more or less the same. You use the same thing. And here I did it for the reflected process. Okay. And we were asking some people if people already knew this. And so far, I haven't found anybody who would tell me where these formulas are written for the reflected case. For the stop case, it seems that they were written. The Fourier transform, even for the reflected case, is written in this book that I mentioned before by Kaslow and Jäger, but it's the Laplace transform. Okay. Now the question that I want to pose to you here is the following, and this is the issue with the simulations that we'll discuss later on, is that once you obtain these formulas, people get overexcited and very happy about them. And sometimes that's a mistake. And I'll tell you what's the story of simulation, which will come later on. So in the case of Iyengar, he was not really interested in simulations. It's a paper of 85, and he was only interested in the applicability of this formula in general. And later on, the Metzler, he was more interested in simulations. Okay. Metzler was interested in simulations. So he looked at this formula, he gets excited with this formula, he says, I need to use this formula to do simulations. And my whole story of this paper in the side of simulation is that when I look at this formula, I don't get very excited about this formula. because, as I said before, if you are going to use this formula for simulations, the first thing you have to realize is that this is an infinite sum. The second thing that you have to realize is that Bessel functions, if you had some experience, Bessel functions are functions that that have expressions with infinite sums, and therefore they are fairly complicated functions. And of course, there are programs to simulate them and to compute them, but you will have to use it for every term. And so this becomes really a complicated issue. And in fact, furthermore, you have signs here, which means that actually these sums are alternating sums. So you have pluses and minuses all the time. And in fact, Metzler tries to use these formulas as much as possible to do simulations. Of course, there are other things in Metzler's paper besides this, but I'm just discussing the simulation side. But essentially, then he finds difficult problems as he can only simulate certain quantities. The quantities that have a relatively easy expression, let's say. And for many other problems that are related with the stopping, then he also says, okay, I can do certain things, but not everything. Okay. And my whole point in this research was to say, well, why, of course, it's good to get excited about closed formulas like this one even, but maybe it's not such a good idea. Maybe you should retain these ones here, right? Maybe you should retain these formulas here and try to use these formulas because these are very simple formulas that have very simple principles, which are these principles of reflection. And this is something that, for example, Professor Akahori has also used in his papers. Okay. But anyway, so my interest again was to say, okay, what can I do for general alpha using this particular case? Sorry. So the question is, what can I do for simulations for general alpha using alpha equal pi over m? Okay, and actually the answer is not so difficult. But before doing that, I would like to also explain another part of the historical side of this thing, which is actually quite interesting, as I said, which is the following. Later, I also discovered another paper. It's a paper by Bañuelos and Smiths, where actually they discuss not only the two-dimensional case, they discuss actually the general d-dimensional situation, again, only with the stop case. Okay, and essentially they find a formula which is very similar to this one here, which is the general formula for a general cone. This is, it's called general d-dimensional cone, because essentially what you do is you take a sphere, and on a sphere you determine a domain D which has a smooth boundary. And then you extend it you put rays so that it becomes a d-dimensional cone. And then the density for the reflected Brownian motion in this case is exactly this one. If you have remembered the formulas that I wrote before, they look very much the same. Let's try to compare. So let me try to use a very interesting function of this application, which is this one here, which allows you to compare formulas. Here it is. So now we can compare the two formulas, and you see that they are very similar. The alpha, this alpha 0 correspond to certain type of eigenvalues. This alpha n is this value here, and these mn's in this case are the cosine functions. Of course, in the case of Bañuelos-Smith, which corresponds to the stop process, these mn's correspond to the sine functions. Okay. And these alpha n's and mn's are nothing else than solutions of certain eigenvalue problems, okay, which correspond again to the Laplace operator, okay, on the sphere with the Neumann condition on the boundary of the domain, okay. And the alpha j's are related to the eigenvalues. So here it is. And if you check everything in one dimension and in two dimensions, you see that everything matches. And again, the question appears here like before. I said, why Bañuelos-Smith didn't do it for reflected Brownian motion? And actually, while trying to do the proof here, I had to find information about this problem here. Okay, and if I remember correctly, the paper of Bañuelos of Smith's, I think is something like 91 paper. Okay, and all the information that I could find about this problem for the Neumann case, is always after 91. So I should be humble and say, well, they didn't do it just because they didn't have, the results yet. The results that are related to this type of problem, because they were dealing with a Dirichlet problem, and here we're dealing with the Neumann problem. The information for the Neumann problem appear much after 91. But anyway, the proof is very similar. And so you have this general formula again. I don't claim that it's a formula that is nice or simple, but it's a formula. Okay. So now let's discuss now the simulation algorithm. And maybe as some of you already guessed, this is not so difficult. But of course, you have to study the properties. I still have to tell you a little bit more about what is the issue of the corner. If you remember, there was a problem with the corner and how we are going to deal with that. Anyway, so this is the simulation method. And although we are talking about wedges, we are going to use an adaptation of something that is called the box method. Okay. The box method essentially says the following. You have a domain, any domain like this, and then you divide it in little boxes like this. And then if you are here, you simulate the process only at the boundary of the box. So let's suppose that you hit here, and then you are in this box here, and then you try to simulate the process again and again. More or less that's the idea. I'm not going to give more details because it becomes more complicated. But anyway, so here I'm explaining one step of our simulation method. So in blue here, you see this is our original wedge. And let's suppose that I am already at the point yn. Okay, I'm already here at yn. So here alpha is general. So it doesn't have to be of the form pi over m. But now I'm going to define an angle theta, which is going to be the largest integer m, so that it can be fitted inside the wedge alpha. And so I start from yn, and now I determine this domain in the dotted red lines, which actually one part is inside the domain and the other part is outside the domain. And I'm going to name this part here nu minus, and this boundary here nu plus. And I'm going to start from yn, and I'm going to simulate where do I end up. So I simulate at the stop process, actually. I could end up with the pink path, or I could end up with the yellow path. If I end up with a yellow path, I will just end up here, and I will still be inside the domain. So there is no, at least in this case, there's no reflection, and you end up in yn plus 1. In the case that you end up in the nu plus, then you have to reflect the process normally, because we are doing normal reflection, and you end up inside the domain. Okay? And then you can keep doing this procedure until final time arrives. Okay? I'll let you think a little bit about the procedure, because if you think a little bit about how this is done, you already realize that, of course, some time is required for this to end. So the question is, how much time I invested here, right? If the time here is long, you will finish very quickly. But if the time there that you spend in doing this path is very short, then you will have to do a lot of simulations. And this is what happens when you are very much close to the edge, because very quickly you will hit one of the two boundaries, and then it will only last a very few times. So the first question that we were asking mathematically is, well, can we prove that actually the time that you will spend doing this will be infinite? And if so, then how can you fix this problem? Okay. So this is what we try to do. But before that, let me again go back and discuss a little bit more the simulation method for stopping, because we are using here, if you see, as I said, in order to obtain the yn plus 1, you are using some simulation method that is related with the stopping. And so let me discuss how this is done in Metzler, and you will realize where the problems are. So we need to simulate the stopping point and the stopping time. So how much time it has elapsed. And so the first thing you do is you are going to simulate in which barrier you arrive. This is very easy because these red dots is symmetrical. So you will end up in nu plus or nu minus with equal probability. And then in Metzler, he gives you actually the simulation method for the radius where you stop. So if you are already in nu minus or in nu plus, you just have to simulate this quantity here, okay, where u is a uniform random variable, and then you can simulate, you know, the radius. Now, the next step is I have to simulate the time, and this is where Metzler has complications. And actually, he's not discussing, of course, the reflected problem, and that's why even this part here does not really appear in the paper. This appears only in the thesis. Okay, and because he was a PhD student, and these were his results during his PhD, and then he's sort of trying to say, okay, I may try to simulate this, but you can do it, but it's not very efficient. This is what he says in the thesis, and the main reason is because the conditional form of the distributions here are actually, as we discussed before, they depend on an infinite sum. And this infinite sum depends on the Bessel functions. Okay. And of course, this is discussed in the general case, for general alpha. Okay. Instead, what we propose is to use a similar formula, but again, it's much easier. Why? Because here I'm only assuming that my angle is of this type, is pi over m. And so I can reduce all my formulas to these exponentials. Okay, the exponentials that I were obtaining before using these Chebyshev polynomials. Okay, and that's why it's easier. And the sum now is finite, and I still have the plus minus signs. And so this is a problem that I also have to deal with, but I deal with it by using some sort of acceptance rejection method. Okay, I'm not going to discuss much about that. If you want, you can ask me later, and then I will explain more details about that. Anyway, so once you have that, then you can start discussing, well, how much time do I need in order to finish this scheme? And the only thing that you have to do, really, if you understood the method, is you have to count the angle. So this is the angle pi over 2 over m, which is this angle here, and you need to count how many times I need to cross these angles so that I cover a final time t. Okay. Now, the study of the law of n is done by using the skew product representation of Brownian motion in 2 dimensions. And I'm not going to discuss too much about that, but anyway, you can do the analysis and you can prove that the expectation of n is infinite. Okay, that actually you need an infinite number of time in order to for the method to really finish. By the way, you can actually prove also that lower moments are fine. Okay, I think if I remember correctly, I think all lower moments than 1 is fine. But anyway, people in simulation don't like the fact that you have mean average time equal to infinity. And so what we propose is an approximation algorithm. The approximation algorithm is as follows. You say, this is the criteria, and this is where the mathematics is. So if at some point in time, I am at any point, and the problem is, what do you mean by at any point near the edge? Well, if this is Rn, okay, and the remaining time that you need to simulate is t minus tn, so you have already simulated up to the time tn, and you want to simulate at the time t. If you satisfy this criteria, which means that you are your Rn is too small in comparison with the remaining time, then you do this approximation. You do this approximation and you end the simulation, okay? This approximation gives you a density in a space. So this is an approximation of the density in a space. And then you just end up the simulation, okay? If you do that, what you obtain now is that the expectation time for the procedure to finish is finite, but of course it depends on this epsilon here, where this power p is in between 1 and 2. And you also can measure now the distance between the approximation that we are using. So this is x bar is the approximation, and xt is the reflected process. And the order of the error in the total variation distance is epsilon. Okay, guys, I don't know how much time I left. I think I'm sort of running late.
Not much, Arturo. We've already gone past, but if you can wrap up quickly, that would be great. Yes.
Okay, good. I'll try to do that. Okay, and then you can also apply this method in order to approximate diffusions on the wedge. Okay, and there are certain problems here that I might discuss if you are interested in, which are related actually with the fact that I have assumed from the beginning that Brownian motion has no correlation, which is the following. If you want to simulate the process with reflection now, I will assume that the diffusion coefficient is 1. And this is the only case I can, sorry, or the identity, if you want, the identity in 2 dimensions. And this is the only case I can do now. And this B here is the drift coefficient. And what I do is something that is called a two-step scheme. A two-step scheme essentially means that first, I assume that there is no noise, and I only do the drift with its local associated local time. So it's like a deterministic movement, but if it hits the boundary, you have to stop it there. And then for the second step, I'm going to do the reflection of the Brownian motion, which I just described before. I can do it in the 2 ways that I described. In the one that takes an average of infinite time, and the correction of it, which takes a finite time, but which depends on a parameter epsilon. So, well, the theoretical results are here. I'm not going to discuss too much about it. So these are the 2 results about the errors. This is the first one where you don't use epsilon. So here there is no epsilon. And here there is the approximation epsilon. And that's why epsilon appears in the result. Okay. Now, we have done the simulations. I'm not going to discuss too much about them. I'm just going to say that some of the things that appear here, of course, Metzler cannot do. For example, if I remember correctly, this simulation Metzler cannot do again because he will have to simulate the stopping time here, and he cannot do that very efficiently. Okay. For example, this one he can do. And so we compare his result with our result, and actually we find out that his method has a bias, which is due to this infinite sums. Okay, but anyway, so these are more or less the references. And as I said, well, the Bañuelos-Smith paper is actually called Brownian motion in cones, and it deals with the stop case, and this is a paper of 97. The book by Kaslow and Jäger, or there are no two Jägers, there's only one, is an interesting book, which actually is a book done by mathematicians, but for engineering. And he's always talking about heat in solids and things like that. And so sometimes you have to translate a little bit the language, but once you get the right thing, you find the formula there. And this is a paper of Iyengar. Again, as I said, it's a paper where I'm not sure that you can consider that the proofs are full proofs, but he gives hints and he doesn't say how to verify the boundary conditions. And then Metzler, as I said before, he corrected some of the formulas of this paper, but he also ignored that these results actually had appeared here. And he also ignored these results that appear already in Bañuelos-Smith's. And then the general situation for oblique reflection was discussed in Vardan and Williams. And actually, I point this out even from the beginning, because I would like to say that actually one of the interests of all this is actually to see if there is anything that can be done in the simple case of, for example, reflection with correlation. Actually, reflection with correlation plus normal, so it's normal reflection, so I should say here normal, is almost equivalent, so I should erase this, is almost equivalent to oblique reflection. And of course, in none of these cases, densities are known, I think, unless somebody can give me some information on that, which I will be very happy to hear about. Okay, so I'll stop here. Thank you very much for the invitation again, and I hope that I didn't go too fast or too far over the time.
No, that's been great. Thank you very much. It's great stuff. Okay. So any questions, comments, anybody?
I have a question. Hi, Arturo. Good to see you again.
Hi.
Hi. I have a question about the formula that you gave for the, so before you were talking about simulations, the formula that you gave about the density of the reflected Brownian motion when the angle is and you have sort of this finite sum. I was just thinking that if no, farther up.
I think it's this one, right?
Yeah, that one. I was thinking that if m is not an integer, let's say, or not rational, you could sort of keep reflecting and keep going in both directions, and you would sort of get an infinite sum, but it would also have to do with the winding number of the Brownian motion. Have you ever
exactly? But no, yeah. Continue.
Well, I was just wondering whether anybody has written that down. I'm not sure if it would be easy to actually write down or not. I just wondered if you did anything.
Yeah, that's an interesting idea, and it's an idea that I have also thought about. But and you could think that actually it's like I don't know what is the name, helix, right? I think it is. Well, what you are talking about is something like this, right?
Yeah, kind of a Riemann surface. If you're
right.
Exactly, yeah.
Yeah, I think people have tried, but I don't think people have gone too far. I know, for example, that people have tried other geometrical structures, and in that sense, is very interesting. And these are related with something that I call the whale tiles, I think it's called. So, for example, one simple example of whale tiles is you take triangles and then you copy them, and then you try to do the same sort of technique. And the question is, when there is some sort of very nice symmetric type of a structure where these things work, but then once you get over it, there is no way of really thinking about anything like this. And also in this case, for example, your question is actually much related with the Chebyshev polynomials.
Okay.
And I don't know. For example, I have tried to search for an expansion of these Chebyshev polynomials that are more related with non-integer sums here. And I haven't found any formula. Maybe there is one, but I don't know.
Okay.
But it's a very interesting point of view, and I think it's still worth thinking about it. But I'm pretty sure that a lot of people have thought about it, and nobody has come out, at least as far as I know, that has come out with a nice idea of how to use it. And I think the whole issue is very simple. Is, you see, just think of something like this, and then you try to think about copying and subtracting, like what I did. And once you have this little piece that goes over the other side, then here you have a lot of trouble of doing the counts.
Yeah, for sure. Yeah.
I thought that Greg asked about the simulation of the winding number. No?
I wasn't really actually, I wasn't asking about simulations at all. I don't know anything.
No, I think he was looking at the formula.
Yeah, Arturo definitely answered what I was asking. I was asking about the formula. Yeah.
Okay. So then I also wanted to ask about the triangle, but you already answered, and Arturo already answered. Because in a just triangle case, you can simply apply your method to get a similar result, I thought, but you said it's not really so.
Wait, no. In the case of whale tiles, like this one, there are some results.
If it is tile whole space, then I think it's, finite. If you finite summation case, but there's also infinite. The tile cannot cover the space.
Okay.
In the case, in similar, the group becomes infinite one.
Right.
Then you have some similar situation. But
right.
I thought that your technique still worked. But I just wanted to ask.
No, yeah, but what do you mean by my technique?
You somehow, the infinite summation, you simulate the infinite summation.
No, I approximate the infinite summation by things that you only have finite summations.
Yeah. So that in a triangle case, it's even in a finite case, the group becomes finite groups. The case where the groups, because it has an infinite summation, infinite series.
Yes.
But actually, in simulating this infinite sum, actually only, this is not really the infinite summation. It is only how to say. Anyway, I just wanted to ask you if it is possible or not.
Well, I don't know, because actually, you see, there is something which is quite interesting, which I comment here if anybody's interested in doing research about it, is so this formula that I just said that I almost completely copied from Bañuelos and Smith is actually the same formula. It's just that they didn't have the right results here. And almost all the results that I use here in order to prove this are results probably from the years 2000. Okay. Now the question, and this is the interesting question, is, well, in all these different possibilities that you have here of generalized cones, how much do you really know about the eigenvalues, the eigenfunctions? And these things actually, there are some very simple cases that appear in the literature, but there are not so many explicit formulas about them. So, for example, in the case of most of the whale tiles, if I remember correctly, nobody knows the explicit form of the function.
Oh, okay.
They know they exist, and that's about it. And maybe, people are trying to prove properties and things like that.
Okay.
But for example, there are certain particular cases that are, if you take squares, then you can do it.
Okay, thank you.
Okay.
All right.
I don't know if you.
Yeah. Any
Go ahead.
any other quick comment or question? I'm just no questions, no comments. Well, if not, please join me in thanking Arturo for a very interesting talk. So, yep, please, thank you, Arturo.
No, thank you very much for the invitation again.
No, thank you. It's been a pleasure.
Hope to see you soon. Huh?
Yes,
I'm
likewise.
getting desperate to really travel with you. You know, in person.
Yeah. You promised you would come to Melbourne, and we haven't been able to organize that. But I'm sure we'll talk to Jiro and we'll try to organize something.
It's our time.